So, we discuss now problem number 21. It says the temperature dependence of a reaction is given by K equals to A raised to the 2 e to the minus E naught by RT. The activation energy EA of the reaction is given by, okay, this is a multiple choice question and it is very simple question. We discussed similar question before. So, it is given K is A T to the 2 e to the minus E naught by RT. So, like before, we will take log of both sides. So, if we write ln k is ln A is a constant here, it is not implied, but it is constant, plus 2 ln t minus E naught by RT. Now, if we differentiate the above expression with respect to temperature, we get d ln k by dt is 0 and this is 2 by t plus E naught by RT square. Now, from Arrhenius equation, we can write K is 8 e to the minus EA by RT. So, again we will take log of both sides. We write ln k is ln A minus EA by RT. Now, again we differentiate this with respect to temperature. So, we write d ln k by dt is 0 plus EA by RT to the 2. Now, if this is equation 1 and this is equation 2, now equating equation 1 and 2, we get EA by RT square is 2 by T plus E naught by RT square. So, we get, if we multiply both sides by RT square, we get is EA is twice RT plus E naught. Okay, so option C is correct. So, option C is correct. Next, we move to problem number 22. It says the rate of decomposition of HI is given with this expression. Okay, so K C square, where K is 4 times 10 to the minus 6 per mole per second at 327 degrees Celsius. How many? Okay, this is problem number 22. Yes, this is problem number 22. Fine. Okay, so how many moles of would decompose A per second at atmospheric pressure? So, if C represents moles per liter and N represents number of moles per cc or number of molecules per cc, number of molecules per cc per centimeter cube. Okay, so then C is n times 10 to the 3 by n. So, dn by dt, and we have minus sign here, is minus n by 10 to the 3 dc by dt. So, it gives n by 10 to the 3 times k times chi square, right. Okay, so minus dc by dt is given here. Okay, so minus dch by dt is given by k times ch square. This is minus dln by dt. Okay, so now we substitute the values here. So we write 6.023 times 10 to the 23. N is Avogadro number we are using here, 10 to the 23 by 10 to the 3 times value of k is given 4 times 10 to the minus 6 liters per mole per second, and then what is the concentration? C by is concentration of H I square. Okay, so this is your 1 by 0.082 times 600 square, right? So 327 degrees Celsius means 600 Kelvin. So if we do it, we get minus del dn by dt is, so minus dn by dt is 9.95 times 10 to the 11 molecules per cc per second. This is problem number 22. Next we move to problem number 23. It says rate constant of a third order reaction at a certain temperature has the value of 0.06. Concentration is in moles per liter and time in minutes. Find the value of K if the concentration be expressed molecules per cc. So instead of moles per liter, it is molecules per cc, and time in second. So basically this is just a conversion of units. So K is given, so rate constant K is given 0.06 moles liter inverse, and this is mole to the minus 2 liter square. Okay, the unit of K in third order reaction. Okay, so mole liter square, mole to the minus 2 liter square, minute to the minus 1. Okay, so 0.06. Now we need to convert this one into molecules. Okay, molecules cc and second. Okay, so 0.06 now per mole is 1000 cc, so 10 to the 3 cc. So this comes, or centimeter. Okay, centimeter cube and square. Okay, so you have L square here, and then moles. Okay, so per mole is Avogadro number of molecules, so 6.023 times 10 to the 23, okay, minus 2 times minute is second, right, 60 second inverse. Okay, so if we further carry out this one, we get 0.06 times 10 to the 6 by 6.023 times 10 to the 23 square times 60, and then this is your c square times molecules to the minus 2, and then second inverse. So we get the value of K, rate constant K in molecules per cc and second. Okay, so K is 2.76 times 10 to the minus 45 cc square molecules to the minus 2, second to the minus 1. So this is just a conversion of units, nothing else here. Now problem number 24, it says a first order gaseous reaction is 25% complete in 30 minutes and at 227 degrees Celsius, and 10 minutes, and in 10 minutes at 237 degrees Celsius. Find the energy of activation and the frequency factor. Okay, so on rising temperature from from 227 degrees Celsius to 237 degrees Celsius, time for 25% completion reduces 30 by 10 means 3 times. So, K 237 by K 227 is degree Celsius is 3. From Arrhenius equation, we know ln 3 is E by 2 we consider in calorie unit, value of R is 2 here, times 10 by 510 times 500, right. Arrhenius equation is ln K2 by K1 is ln K2, so K is A e to the minus E A by RT. Okay, so if we consider this, then ln K2 by K1 is E A by R 1 by T1 minus 1 by T2, right. So, here T1 is 227 degrees Celsius means 500 Kelvin, and T2 is 237 degrees Celsius means 510 Kelvin. Okay, and value of R is in 2 calorie per mole per Kelvin we are using here, and per Kelvin, and E is the activation energy we are also considering. Okay, so if we do it, we get EA is 2 times ln 3 times 510 times 500 by 10. So, we get the value of EA. So, EA is 55.665 kilocalorie per mole. Okay. Now, at 227 degrees Celsius, because we need to calculate frequency factor. Okay. So, at 227 degrees Celsius or 500 K temperature, okay, so K is 1 by 30, because in 30 minutes, so 1 by 30, and then ln A by A minus 0.258, 25% completion. So, we get the value of K is 1 by 30 times ln 1 by 0.75. So, if we do it, we get the value of K is 9.6 times 10 to the minus 3. This is first order reactions, we are using the expression for first order reaction. This is for first order reaction. So, value of K we have got, A we have got, and now we have to calculate A. This is very simple. Okay. So, again, according to Arrhenius equation, so K is A e to the minus E A by RT. So, value of A is K times e to the E A by RT. So, A is value of K we have got 9.6 times 10 to the minus 3, and this is in minute inverse. So, this is minute inverse, then e to the EA, value of EA is 55,665. This is in calorie unit, divided by R is 2 and T is 500, we are considering 500. So, if we do it, A, we got 2.07 times 10 to the 22 second inverse. So, we convert this is minute inverse into second inverse. Therefore, the frequency factor A is 2.07 times 10 to the 22 second inverse, and this is the value of activation energy. This is the value of activation energy. So, this was problem number 24. Now, problem number 25 says a drug is known to be ineffective after it has decomposed 30%. The original concentration of the sample was 500 units per ml. When analyzed 20 months later, the concentration was found to be 420 units per ml. Assuming that the decomposition is first order, what will be the expiration time of the sample? What is the half-life of the drug? Now, original concentration of the drug, it is given, right? Original concentration of the drug is 500 units per liter. So, original concentration of the drug is 500. So, this is, if we say this is your concentration of A naught rather, okay, is, or concentration of A, if we say A is 500 units per ml, and after 20 months the concentration of the drug is 420 units per ml, right, and the decomposition is first order. Since the decomposition is first order, so it follows first order kinetics. So, we can write K, the rate constant K, is K is 1 by T, T is 20 months, okay, and ln 500 by 420. This is your months inverse. Okay. So, if we calculate this one, we get 8.72 times 10 to the minus 3 month inverse. So, this is the value of K. Once we got the value of K, half life we can easily calculate. So, the half life of the drug, we will first calculate the half life period. So, the half life period of the drug if we consider T half is 0.693 by K. This is in months now. So, you get 0.693 by 8.72 times 10 to the minus 3 months. So, if we calculate this one, we get 79.47 months. So, this is the half life period. Now, what will be the expiration? Okay, so it will be ineffective after it has decomposed 30%. When the decomposition is 30%, then it will be ineffective. Okay, so after 30% decomposition, the concentration of the drug will be, so initial concentration was 500 and 30% is getting decomposed, so 500 times 30 by 100, this is units per liter, units per ml, not liter, milliliter. So if we calculate this one, we get 350 units per ml. If T is the time taken for the drug to be ineffective, then we write T is 1 by K ln 500 by 350. So value of K we have already got, so we get 1 divided by 8.72 times 10 to the minus 3 and ln 500 by 350, and this is in months. So we get value of T is 40.9 months. So this is the time, taken by the drug to be ineffective. Okay, this is the time taken by the drug to be ineffective. Now problem number 26, it says the gas phase reaction CO plus Cl2 gives COCl2 is second order. So first order from each reactant. Okay, so if the P naught CO equals to P naught Cl2 equals to 0.1 atmosphere and T half is 1 hour at 25 degrees Celsius, but 30 minutes in 35 degrees Celsius, then first problem is calculate K at 25 degrees Celsius. Remember this is second order reaction, okay, and but first order with respect to each reactant. Calculate E means activation energy and A of the Arrhenius equation, and delta is dagger and delta is dagger of the transition state treatment. So it consists of several problems. Okay. Now what it gives? Okay, it says. Okay, so it says the so first order reaction kinetics. Okay, so for second order reaction, T half is 1 by Ka, where A is concentration, initial concentration, right? We consider A is initial concentration. As we discussed before, so for second order reaction, T half is inversely proportional to the initial concentration of the reactant. Okay, initial concentration of the reactant. Right. So we can write K is 1 by T half times A, right. Now at 25 degrees Celsius, if we say K, rate constant K is K25, the rate constant K is K25, then we can write K25 is 1 by 60 times 0.1 atmosphere inverse minute inverse, right. So, 0.1 is the atmosphere here, 0.1 atmosphere initial concentration, and it is given rate constant 60. Okay. Okay, so we get the value of because 1 hour, right? It says T half is 1 hour here. So 60 minutes we are converting. So hour to minute here, and then this 0.1 is the initial concentration. Here it is pressure P naught. Okay. So you get, and then similarly at 35 degrees Celsius, the rate constant K is, if we say K35, then K35 is 1 by 30 times 0.1 atmosphere per minute. Okay, so for the previous one we get 0.167 atmosphere inverse minute inverse, and here we are getting 0.333 atmosphere inverse minute inverse. So the half-life periods we have got. Okay, from the half-life periods we got the actual rate constant. Okay, we got the rate constant. So calculate K value we have already got. Now we know ln K35 by K25 from the Arrhenius equation. Basically we get EA by R and then 1 by T1 minus 1 by T2. So what is the value of T1 and T2? So T1 is 25 degrees Celsius, means 298 K, and T2 is 35 degrees Celsius, means 308 K. So K1, K25 and K35 we know. So ln K35 by K25, so 0.333 by 0.167 gives you EA by R, and value of T1 is 298 minus 1 by 308. So this gives you 2. So EA gives, value of EA is 298 times 308 divided by 10 divided by 10 times ln 2 times R. So value of R. So we get EA. Value of EA we have got is 12586.57 calorie. So this is the value of EA. So this we have already calculated. Activation energy, that's also we calculated, and then we need to calculate A, means pre-exponential factor A. So we know ln K, suppose 25 is ln A minus A by R times 298. Okay, so we get ln A is ln K25 value we know, so ln 0.167 plus EA value we know 125.86 by 2 times 298 So, we get value of A is 4.74 times 10 to the 6 second inverse. Right, this we will get is atmosphere inverse second inverse. So, this is the value of A that we can calculate. Okay. Next, we need to calculate delta H dagger and delta S dagger. So, when we compare collision theory and transition theory, so when we calculate collision theory and transition theory and transition state theory, we get we see delta H dagger is E plus delta N E plus delta N minus 1 times RT. So, we use the value of E. E is nothing but EA. EA is 12586.57 and minus what is the value of delta N here? So, delta N is plus delta N is basically reactant, product minus reactant. So, 1 minus 2 minus 1 RT. Okay. So, we write to 12586.57 minus this is minus 1. So, we get minus 2. Okay. So, minus 2 times R. So, value of EA is calculated using calorie unit. So, we need to use again calorie unit 2 times 298. So, we get 11402.32 calorie per mole. So, this is the value of delta H dagger. Now, we need to calculate delta S dagger. Okay. Again we know rate constant K25 is Kb is the Boltzmann constant times T by H is the Planck constant e to the minus delta H daggered by RT times e to the delta S daggered by RT. Okay. Now, if we substitute value of K25 is 0.167 atmosphere inverse minute inverse, and value of KBT also we need to use. So, if we convert this one into atmosphere into second, so we get 2.78 times 10 to the minus 3. So, this is atmosphere inverse second inverse, and value of Kb. Okay. So, Boltzmann constant we know Kb is 1.38 into 10 to the minus 16 in arcs unit, okay, arcs per degree, okay, arcs per degree, and then H is also known in arcs. So, 6.62 times 10 to the minus 27 in arcs unit. You can use in SI unit also. So, you can use 23 and this is 10 to the minus 23 in joules per degree, joules per Kelvin, and here also you write 6.626 times 10 to the minus 34 and then joules second. Okay. Now, if we use all these value even for delta H dagger we have also calculated. So, if we all put those values, we get delta H dagger is minus 32.02 calorie per Kelvin. Okay. So, this is the value of delta H daggered and this is the value of delta H daggered. Next we move to problem number 27. It says at 25 degrees Celsius the specific rate constant for the hydrolysis of ethyl acetate by NaOH is 6.36 liters per mole per minute. Starting with the concentration of base and ester of 0.02 moles per liter, what proportion of ester will be hydrolyzed in 10 minutes? Okay. So, what is the value of K here? Okay. So, the rate constant K here is 6.36 liters mole inverse minute inverse, right. Now, from the unit of rate constant, we find that this is a second order reaction, right. From the unit of the rate constant, we find the reaction is second order. Okay. For the second order reaction, rate constant is liter per moles per minute. Okay. So, from the rate law we write K is 1 by T x by A times A minus x. A is the initial concentration, okay, and x is the concentration at time t. So, if we substitute the values now, so 6.36 is 1 by 10 because it hydrolyzed. We need to calculate proportion of ester will be hydrolyzed in 10 minutes. So, 1 by 10 and then value of x by 0.02 times 0.02 minus x. So, okay, so we get value of x is 0.011 moles per liter. So, percentage of ester hydrolyzed. So, percentage of ester hydrolyzed is 0.011 by 0.202 times 100. So, we started with 0.02 and this is we got the value of x is 0.011. So, 0.11 by 0.02 times 100. So, we get roughly 55%. So, we move to problem number 28. It says at 25 degrees Celsius the half life for the decomposition of N2O5 is 5.7 hours and independent of the initial pressure of N2O5. Okay. So, half life does not depend on the concentration of N2O5. Okay. So, it says the rate or the reaction is of first order, right. It's first order reaction. So, calculate the specific rate constant and time required to go to 90% completion. So, only trick here is, okay, since it is independent of initial pressure of N2O5. So, since the half life is independent of the initial pressure of N2O5, so the order of the reaction is first order. Okay. So, since the half life for the decomposition of N2O5 is independent of the initial pressure of N2O5. So, the decomposition of N2O5 is first order. So, if it is the first order, half-life is given and we need to calculate the rate constant. Okay. So, first part is very easy. So, the rate constant for the decomposition of N2O5 is, so K is 0.693 by T half, right. So, value of T half is given 5.7 hours. So, 0.693 by 5.7 hours in hour inverse. So, if we calculate this one, we get 0.1216 hour inverse. So, this is the first part. This is very easy. And see, once we got the value of K, we can actually calculate the time required to go to 90% completion. 90% completion means 10% remaining, right. So, for the first order reaction, T is 1 by K ln A by A minus X, right. So, T is 1 by K, K is 0.1216 ln 100 by 90% completion. So, you get 10 here. Okay. So, 100 minus 90. So, if we calculate this one, T, we get 1 by 0.1216, then ln 100 by 10. So, we get T is, if we calculate this, T is, we get 18.94 hours. This is the answer. Now, problem number 29, it says at 378.5 Kelvin temperature, not Kelvin, Celsius, the half-life for the first order thermal decomposition of ethylene oxide is 363 minutes, and energy of activation of the reaction is given 52000 calorie per mole. So, from this data, estimate the time required for ethylene oxide to 75% decomposed at 450 degree Celsius. So, we need to calculate the rate constant at 450 degrees Celsius from the value of EA and other data. Okay. So, EA is given. So, EA is activation energy, EA is 52,000 calorie per mole. Okay. So, activation energy EA is 52000 calorie mole inverse. T1 is given, T1 is 378.5 degrees Celsius. So, we need to convert this one into Kelvin. So, we get 651.5 Kelvin. T2 is also given. Okay. T2 is, what is the value of T2? It is 450 degrees Celsius. So, we get 723 Kelvin. What else is given? It is given half-life period for the first order is half-life period is given. So, K1 is 0.693 by 363 minute inverse, right. So, we need to calculate what is the value of K2. So, ln K2 by K1 is EA by R 1 by T1 minus 1 by T2. So, we get ln, what is the value of K2? K2 we need to calculate. K2 by value of K1 is 0.693 by 363 equals to value of EA is given 52,000 in calorie unit. Okay. So, by 2, and then 1 by T1 is 651.5 minus 1 by 723. So, if we calculate this one, we get the value of K2 is 0.101 minute inverse. So, we got the value of K2. So, we need to calculate now the time required. Okay. So, the time required for ethylene oxide to 75% decomposed so this value of K2 is at 450 degrees Celsius, right? 75% decomposed is T is 1 by K2 ln 100 by 25. So, value of K2 we just calculated 0.101 and ln 4, this is in minute. Okay, so, if we calculate this one, we get T is 13.7 minute. So, this is the time required for ethylene oxide to 75% decomposed at 450 degrees Celsius. Problem number 30 says the rate constant for a chemical reaction is 2.3 times 10 to the minus 2 per minute at 27 degrees Celsius. Compare the rates when the reactant is decomposed to the extent of 25% and 50% respectively. What time will be necessary for the complete reaction? So, the rate constant value is given. So, the rate constant is 2.3 times 10 to the minus 2 minute inverse. Okay. So, the unit of rate constant K. Okay. So, the unit of rate constant K indicates a first order reaction, right? A first order reaction. Okay, so if C is the concentration of a reactant at any time t, then R, rate R, (2.3 times 10 to the minus 2 minute inverse). Okay. If C naught is the initial concentration, then after 25% and after 50% decomposition, remaining amounts are, so when 25% getting decomposed, so remaining amount is 0.7, okay, or 75% and 0.50, right. So 0.7, so initial concentration of C naught, so the so this is 0.75 C naught and 0.50 C naught. So R is, or R1, if we say R1 is 2.3 times 10 to the minus 2 times 0.75 C naught. Okay, so you need to multiply this with C actually. Okay, so this is C naught. and then R2 is 2.3 times 10 to the minus 2 times 0.5 C naught. So, R1 by R2 is 2.3 times 10 to the minus 2 times 0.75 by 2.3 times 10 to the minus 2 times 0.50. So, we get 1.5, they get cancelled, you get 0.5. Okay, so as it is a first order reaction, it will be completed only after infinite time. That is incomplete. Why? Because we know A is A naught times e to the minus kT. So, A, concentration of A goes to 0 when t goes to infinity. So, if t goes to infinity, e to the minus kT gives goes to 0. So, when t goes to e to the minus kT goes to 0, right? Only then, okay. So, you get concentration of A is 0. Concentration of A is concentration of the reactant at time t. So, concentration of reactant at time t means concentration of A, it goes to 0 when t goes to infinity, because when t goes to infinity, e to the minus kT goes to 0. Okay. So, at infinite time only the reaction will be completed.